Yeah. Coming to the this week's problem solving session, there are the topics related to big game method, two phase method, and some different types of solutions in an LPP problem. So while coming to an big game method and also two phase method, I'm just asking you that when we can use big game method and two phase method, why we are tending to use those methods. Any one of you can answer to unmute yourself, or even you can say in a chat box also. I'm again asking you when we can use become method and then two phase method. In an artificial case, one answer is an artificial case, yes, of course, but why? Even in the artificial case also, why we are using? Why we are tending to use, especially in become method or two phase? By the previous methods? Yeah, almost you reached to the, but not exactly in the previous methods that we can just first we need to convert the initial problem into a standard LPP, right? So while converting into the standard LPP, sometimes we need to convert the constraints into an equation. So while converting that constraints into an equation, we may tend to take slack variable or surplus variable, right? So the basic solution how obtain means, so we assume that the artificial decision variable coefficients are zero, and so that whatever the solution we are obtained are the basic solution, initial basic solution. And what our assumption is the solution must be non-negative in initial level or final level. It should be non-negative. If it should be negative, then we what we have to do in that case? We are failing to move the next forward, right? So in that case, we can use bigger method or two-phase method. I can explain to you in detail that if we have a problem that suppose we have a problem like this, or 3x1 plus 2x2, and subject to the constraints x1 minus 2x3 is less than or equal to 5, and 2x1 plus 5 x2, here also x2, greater than or equal to 6, x1 x2 greater than or equal to 0. Now in this case, how we can convert the given constraints uh, into the into the equations? First here it is a less than or equal to constraint. So what we have to do here? We have to add a slack variable or subtract it with the surplus variable. Okay, sorry. Okay, now is the screen visible? Yeah. So in this type of problem, how you can convert the given constraints into the standard form? For the first constraint, how you can convert this into an equation? Yes, please. Add surplus variable. Okay. So in the first case, there is a less than or equal to constraint, so that we are adding a slack variable here. That is, I am assuming s1. In the next second case, 2x1 plus 5x2 and minus s2 is equal to 6. Here s1, s2 are the slack and surplus variables. So to get the basic solution, I mean basic feasible solution, what is an assumption that x1 and x2 are equal to 0. So that what we have to get, s1 is equal to 5 and minus s2 equal to 6, right? I'm sorry, here s2 equal to 6. So in this case that means s2 equal to minus 6. This is not greater than or equal to 0, right? So how we can move into the forward? So in this way we are failing to move forward with the simplex method. In this case, there are the two alternatives to solve this type of questions. That is, when the constraint is the greater than or equal to type. That means in some cases the basic feasible solution is not available. So that we are tending to use the big M method or two-phase method. That means there is a in this case we needed to add a artificial variable, so that we are also assuming that s1 in the first constraint we can get s1 is equal to 5, but in the second constraint we assume that s2 is also equal to 0, so that a1 is equal to 6, right? A1 here, a1 is an artificial variable, so that we are getting a initial basic feasible solution to an artificial variable. So here we are introducing a concept or another variable, that is an artificial variable. With the help of artificial variables, we can solve this type of linear programming problem by the big M method or two-phase method. Okay. So all you had cleared that when we can use big M and two-phase method, right? Is anyone have queries? Okay. So coming to these two methods, how we can solve means, first I tell you the procedure of these two methods. First we discuss that in a simplex method, what is our objective function? Objective function is looks like maximum or minimum of z, objective function that is equal to the some cost coefficients and decision variables. If we add the slack or surplus variables in a simplex method, then that coefficients should be 0 in an objective function, basic objective function in the simplex method, right? But in while considering the bigger method, we just take that the objective function in an objective function that the coefficients of an artificial variable as minus m. That is some penalty we are adding there. And become there is another name to the become method is Charles penalty method. Here the cost coefficients for decision variable and 0 for the slack or surplus variable and minus m as the coefficient for an artificial variable. Here I am saying artificial variables. Here these are slack or surplus. Is this all you are know, right? And whereas coming to the two-phase method, the objective function, there are the two phases while considering a two-phase method by the name itself. First, we consider the first one case that in this case we take the all the coefficients for the decision variable and also the slack or surplus variable as zeros, but only we consider that an artificial variable's coefficient as minus 1 to the artificial variable. In the first phase, while completing to the first case and entering into the second phase, in a phase 2, I am just showing you the difference in each phase in the objective function. While in the second phase, the objective function has the initial, whatever the cost coefficients initial problem, that is the cost coefficients and decision variable, like the previous, and 0 into slack or surplus. So these are the differences to the simplex method, figure method and two-phase method in the expression of objective function. And then in bigger method, after considering in this type of objective function, then in bigger method I said that objective function is max or minimum is equal to cost coefficients and decision variables plus 0 into slack variables or surplus minus m into artificial variables. So while coming to the simplex table, in each iteration, what is the criteria to for the entering variable in a bigger method? Is there any difference to the bigger method and simplex for an entering variable and leaving variable case? Yes, please, anyone? In a bigger method, what is the criteria for an entering variable? Yeah, any other? Please respond. You can also answer in a chat box. This is not a one-way topic. You can also discuss and Ask any of your questions. Okay, let me tell you that the criteria of an entering variable is same as previous, yes, of course. But in a deviation row, we might have a coefficient as m. Previously, we used what is the criteria that largest deviation, which variable had the largest deviation, that should be the criteria to the enter into the basis. But here we have with the m's. So in this case, how we can deal? I guess everyone has understood as maximum deviation entry. So in the maximum deviation entries rows, there is an involvement of m. M means penalty. We are not assuming any of the values m. Yes, into the basis. So m means we can first, there are the more m variables involved, m type of variables involved. So for suppose the x1 variable has the deviation row, there is an m minus 1, and the x2 variable has 3m minus 2, and x3 variable has 4 minus m. So in this case, which variable has the criteria to enter into the basis? Mm-hmm. Yeah, some others. Is there any different answers can I expect? So here, by the name itself, we are saying the maximum deviation entry. So first we need to check trial and error method. That if for suppose m is equal to 1, then for x1 case it's 0, and in the x2 case it is 3 minus 2 1, and x4 case it is 4. Then how you can say that x2 has the maximum value? Sorry, here. Yes, 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 of course. If we take m as large, that means m is equal to more than 4, or that means if m is equal to 5, then most number of the cases we had 5 minus 1 4 here, and here 15 minus 2 13, and minus 1, right? In this case, the maximum value occurred at x2 case. So to only the cases 1, 2, 3, or 4 we can take, we observe that x3 has maximum. And in any other cases, we have the maximum as x2. So as considered most frequent maximum value is x2. X2 has the most frequented maximum value. And next, what is the criteria to leave the basis? Criteria that a variable to leave the basis. What? Who said? Yeah, minimum ratio test. How we could proceed with the minimum ratio test? And Uday Kumar asked that how to find entering first variable during first iteration in simplex method. Uday, did you clear? Just now I explained that the criteria of an entering variable. Entering variable must have the maximum deviation as compared to the other variables. And for the leaving variable, we must have the minimum ratio test we need to follow. So that minimum ratio test means, for suppose here we had an RHS. So here RHS divided by xk. So suppose here this is the living variable. In this case, whatever the variable we had, that is an xk. Or all the pivotal column elements are considered as xk. And here RHS divided by xk, and that xk is also must be greater than 0. So in this case, which of the row value has minimum, that is the criteria to leaving variable. So that means minimum of the ratio test, ratio between RHS and the elements of the pivotal column. And if this xk, here we are assuming that xk is greater than 0. If xk is equal to 0 or xk might be negative, then what would happen? Yes. You can say xk equal to 0 or xk less than 0. In these two situations, what we can say? Even in the simplex method or any of the LPP problem. Okay. If all of the rows have the same situation, then whether you understood that, I said that each of the elements has the same situation, that xk had value 0 or less than 0. That means here we may get the 0, sorry, infinite or minus 1 negative values. Okay, no solution. That means we can express that as an unbounded solution. Generally, with a graphical method, we can easily say that whether you can find an unbounded solution or infeasible solution or optimal solution, that is multiple solutions. Easily you can find through the graphical solution. But in an LPP problem, there is a criteria that for an unbounded solution, that means that minimum ratio test fails. Minimum ratio test fails means any of the xk has zero value or negative values. In that case, we can say that the LPP has an unbounded solution. After this, is that clear? Okay. And next, coming to the two-phase method. First, in the two-phase method, our objective, we made an objective function as minimum or maximum of the should be has first initially the coefficients of the decision variables also should be zeros, and slack or surplus variables also zero, variables coefficients, and only we give -1 for an artificial variable. So there is a criteria that the in a phase 1, what is the stopping rule for a case 1 and how we can enter into the phase 2. Stopping rule for phase 1. Anyone can answer this. All the artificial variables has out, then we can enter into the phase 2, right? You said. Uh, okay, others? Others? If you had queries also, you can ask. So the stopping rule in phase 1 has the criteria that all the artificial variables has to be leaved out, and also we are taking the two-phase method only that in the basic assumption of minimizing the artificial variables, so that whenever all the artificial variables has come out, there is a one stopping criteria of phase 1, and also when the temporary objective function, all the temporary objective function deviation rho has the values of 0, then also there is a criteria of stopping the phase 1. Whether you understand what I said? In the deviation row, if all of the uh, variables deviation row entries are zeros, then also we can stop the phase 1 and then enter into the phase 2. And what is an advantage of the two-phase method as compared to the big M method? In case of, you can say, in case of considering artificial variables while doing in a problem, which one is most easiest you think, or why it is? Both methods we use in the same purpose only. Okay, why you think that, how you think it is easier than begin? Okay, another who? Okay, okay, and is there any other? Okay, I tell you. In the two-phase method, whenever the artificial variable is leaving from the basis, we just crossed out that artificial variable uh, from an iteration table. So there is a less number of calculations. Why? Because we are eliminating the entire column of that artificial variables in each iteration by iteration. That means the less number of calculations are included. And why we are most tending to use the two-phase method? Because in as Adarsh Dubey said, the bigger method has we need to know the values of m. Then only you can perfectly tell which is the living variable also. But here we can easily say there is no need to know the value of m. So in a computer oriented thinking, in a bigger method, we only manually have to take the m values also. While doing it in a computer, the computer also has to assume that more number of the m values and it has to give which is a living variable. But in a two-phase method, we only had the 0 or 1. That means computer can read these numerical values easily and then it can give the answer quickly. That's why also the two-phase method has more advantages than the bigger method. And next, in the okay, stopping rule is over. Then coming to the phase two. Previously, I said that in the phase two, the objective function looks like what are the coefficients we can take for decision variables. I am asking why, because previously I said, and for slack variables, slack or surplus, and is there artificial variable? In the phase 2 method, while considering an objective function, what is the coefficients for a decision variable, slack or surplus variable, and artificial variable? Plus, for the surplus variable, in the objective function, are you saying in an objective function or decision or constraint? Okay, okay. Whatever you said for the decision variables is correct, but think about the slack and surplus. Yeah, of course. As in the simplex table, here the phase in the phase 2 method, we have the coefficients of decision variable as 0 and also, sorry, the initial basic coefficients, whatever we had that cost coefficients that are, and in the slack and surplus variable, we had 0 so like the simplex table, initial simplex table, and there is no artificial variable pair because in the phase 1 only we are crossovering this artificial variables. That means we are minimizing the total artificial variables. Is it okay, Dubey? Yeah. So these only the differences between um, bigger method and two-phase method. And next coming to the different situations in an LPP, that is multiple solution of an LPP, and what are different solutions we can obtain? Unbounded solution. Did you face any other solution? Infeasible solution. Uh, okay. Previously I said when we get an unbounded solution while going through an LPP problem. right? Let me know who is who are concentrately listening when we can obtain an unbounded solution in an LPP. Okay, that means uh-huh. Sorry. Okay, and minimum ratio test fails means when it can fail. Okay, is all of here are agree with the. You can also text in a chat box. Okay, so whenever the minimum ratio test fails, you can say that there will be an unbounded solution while saying in an LPP problem. And when we can tell that an LPP has a multiple solutions, come again. Hmm. Okay, think once what you said. Who others? Okay, so in an LPP, when we can say that the basic variables, non-basic variables also. First, we can start with what is the basic variable in an LPP or and what is the non-basic variable. First, we must first, first we must know these differences. Right? Yeah. So in an LPP, we had for suppose we had n number of decision variables and we had m number of constraints, one, two, and m number of constraints. So we just convert all these m number of constraints. We assume that only these constraints are less than or equal to or greater than or equal to type, but not in an equation form. So in this case, we can get an m number of slack or surplus variables for each the constraint, right? So n decision variables and m number of constraints, so that we had the m number of slack or surplus variables. So in this case, overall we had m plus n variables that can get a chance in a simplex table. So in this case, you can say that all these n variables, you can say these are the basic variables. That means these n variables had a zero valued or basic. And whatever the non-zero valued, are non-basic variables. That means the non-zero valued variable means in the respective constraint it has the coefficient 1 and in all other constraint it has the value 0 for the non-basic variable. What I meant to say, I think you understand. For suppose the constraints are x1 plus x2 less than or equal to 2 and x3 minus okay, x1 minus x2 greater than or equal to 5. So in this case, how we can convert these into an equation? X1 plus x2 minus s1. So this is less, so slack variable that is equal to 2 and x1 minus x2 minus s2 is equal to 5. So in the respective constrained equation, the slack variable s1 has coefficient. If we can see that in a matrix form, it is x1 1 1 and s1 has 0, x1 x2 and these are s1 and s2. x1 coefficient 1, x2 has 1 and s1 1, and in the other case s2 is 0. 1 minus 1 0 minus 1, right? That means in its respective constraint it has the value 1 and in the other cases it has the value 0. That type of variables you can say that are the non-valued variables that we can say the, and while considering if as the initial basic feasible solution, we consider that x1 x2 the basic variables has the solution 0 and s1 s2 has the respective cost coefficients as 1 or minus 1. I mean in the equations we had here s1 is equal to 0 and s2 is equal to minus 5. So to convert this we just take an artificial variable in this case. While using a big M or two-phase method we can solve it. But here you can say that these are the s1 and s2 are the basic variables. If we had an artificial variable then you can say s1 s2 and other artificial variables are included. So in this case s1 is the s1 is the basic variable and other here an artificial variable would be included, that would you can say it as a basic variable. Sorry. So whenever the coming to the multiple solution of an LPP, whenever the non-basic variable have the zero values in the deviation entry row, we can say that that LPP has multiple solutions. And not the basic variable, it's non-basic variable. And coming to the infeasible solution, when we can say that an LPP has infeasible solution. Anyone can? I am giving you the time to think and answer it also. Okay, let me tell you. Yeah, yeah. Yes, of course. So whenever the artificial variables are still included in the basis, but we are attaining the optimality, then you can say that an LPP has the infeasible solution. So let's see an assignment, I think is this screen also visible, right? Is everyone able to see? Okay. Here is a question that if during an iteration of simplex method, the minimum ratio test fails, then the LPP has which of the following is you are assuming? I also previously tell that. Mhm. As so I can say that in an during the iteration of an simplex method, the minimum ratio test fails. That means there is an unbounded solution. So here unbounded solution and next thing. I think you understood the next second question that if during the last iteration of simplex method, the entry corresponding to the non-basic variable in the deviations row is 0, then the LPP has, that means in a deviation row, the non-basic variables had the 0 value. Yeah. Everyone, please answer it. Even in the chat box. Yes, Kurti Aravind previously raised a question. Others, please. Okay. So I'm repeating again that when the deviation non-basic variable in a deviation row has still in 0 values, then we can say that that has a multiple solution. And next, third question, if the optimality has arrived, but the artificial variable is still in the basis, then the LPP has no solution. Previously, okay, here the options are no solution, multiple solution, unique solution, and unbounded solution. Uh, but this is specifically we can define in another way. No solution means, in other words, okay, again think infeasible or feasible. I am expecting to receive answers from all. Yeah, yeah. infeasible solution means we can't tell the solution to that problem. Both are same. Yeah. In other words, we are saying that it has no solution. Okay. Here it is an infeasible solution. When an artificial variable is still in the basis, but optimality has arrived. Optimality has achieved means in the deviation row we are getting all the entries are maximum, I mean positive values or zero, right? That means you can say that in the last iteration simplex method, the optimality uh, can be achieved. And next, and an artificial variable is added in the constraint when generally in a linear programming problem, if the our constraints are greater than or equal to type, then we can add an artificial variable to just get the first initial basic solution, right? I only told you the answer. Okay, which is you can, so you can say that a readily available basic solution is not available. Then only we are making to add an artificial variable to in the case of greater than or equal to constraint. Okay, next. I guess everyone must answer this. For a maximum LPP during the simplex procedure, the criteria for a variable to enter into the basis. Uh, so many, yeah, who told? Okay, so many times we had discussed it that the criteria for a variable to enter into the basis. Minimum deviation entry or maximum deviation entry. Mm. And next, then what is the criteria for a leaving variable? Not the minimum deviation entry. Okay. Is everyone fine with this? And mm, in a two-phase method, the objective of the first phase is okay. That means in a first phase, we are eliminating the artificial variables. From that also we can say that we are minimizing the sum of artificial variables. And in the two-phase method, the objective of the second phase is first one is use the basic feasible solution uptime after the completion of phase 1 as a starting basic feasible solution for phase 1, or the basic feasible solution obtained after the completion of phase 2 as a starting basic feasible solution for phase 1. I think you guessed that. Whatever the basic feasible solution obtained after the completion of phase 2, is this the starting basic feasible solution for phase 1? Without the completion of phase 1, how can we enter into the phase 2? So this is no. And use the basic feasible solutions obtained after the completion of phase 1 as the starting basic feasible solutions for the phase 2, or none of the above. Yes. Okay. Because I already told up to now all these, that's why I'm going little faster. And then the difference between the what are the differences between the big game method and the two-phase method? The row entries corresponding to the constraint in various iterations or tables are the same. That means in the two-phase and also big game method, the row entries corresponding to the constraints are same, and the basic feasible solution at each iteration is the same. At each iteration in the two methods. Is this the difference, or the solution obtained by both methods is same? Yes, this is of course these are true, right? The solution obtained in the two phases, two methods are same. Then only can say that our assumptions and all of our theories are correct. And the row entries corresponding to the constraints in the various iterations or tables are the same. Yes. And entries in the top row corresponding to the coefficients of the objective function are not same. Top row means the objective function, the coefficients are not same. Who told previously? Yes. So far I explained you that the difference comes from these two methods only from the objective function. Not only that means the objective function in an objective function, the Becker method has a coefficient as minus m for an artificial variable. And in the two-phase method, for the phase 1, we had the coefficient of artificial variables as minus 1, and also the coefficients for the decision variables and like a surplus variables we considered as 0. But in phase 2 of the second two-phase method, we considered an initial coefficient as here. So you can say that the coefficients of the objective function are not same. That is the major difference between big game method and the two-phase method. Up to now, all are fine. Okay, I think we're coming to the time. Okay. If you had any queries, can please ask. So up to this, the today's session topics were covered. Uh, Up to this last question, which else you can ask from this. For the last question, D1 is D option. The difference is only in the objective function. D is the correct option. This I take because of the solution obtained of the both methods is same, of course. That's why I mentioned. Is it clear, Aarti? Okay. Okay, then let's meet in a next session. Yeah? Yes. Yes. Yes, yes, yes. Actually, this option was not entirely correct, but this is not the difference between these two methods, right? Yes, 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 yes. Not in all the iterations, but in initial iteration, we can had the constraint entries are same. Hmm. Thank you, sir. Okay, good night to all.